I promised you today that we would have the best lecture of the course, which is true. And what is actually true, I don't know whether it'll be the best lecture, but it's about the best topic in the course, and one that is incredibly fascinating. And in particular, we're going to talk about what happens when those timing constraints that you've learned about for building these synchronous machines are violated. And it's going to turn out that some of the time in computers, because they interface with the real world, we are forced to violate those constraints. And we're going to understand a little bit about stuff, even going down to basic physics, about what it means when those constraints are violated and how they resolve. But let's begin with a little bit of review, taking a look at some of the timing that you've been learning about in the last, at the end of the last week. So if you remember, here we have a typical synchronous finite state machine, and it consists of some combinational logic and input and output and some feedback that, if you remember all of our examples, goes through a synchronizing delay or memory element, which is this flip-flop right here, clocked by the clock. And if you remember that there were certain constraints on the timing having to do with this feedback loop right here. And the first constraint was one saying whether or not the loop would work at all. And it was a question of, as soon as this clock goes off, then contamination begins to affect this Q output here. And as soon as this gets contaminated, then contamination flows through the combinational logic and comes back around here. And we wanted to first ensure that that kind of wave of contamination that goes through here did not happen too quickly. Because after all, just like a camera, we're blessed with an expert here on cameras, there are setup and hold times for this flip-flop. In other words, the picture of the data that we're going to take has to stand still when we click the shutter here. And Phil, even before you came, I was talking in these terms. And thank you. And so this contamination race is basically saying, don't have the contamination race around back to the lens here before the hold time has passed. And what that says is that the hold time has to be less than the sum of the contamination from clock to Q of the register here and the contamination delay of the combinational logic over here, which is how fast we can race around here. Okay. The second constraint that we had with regard to timing was when we could click the shutter the next time, which is a question of when does the new data about the next state or the next state come around through the combinational logic in order to get back to D. And if you remember, there we were talking about the propagation delays, or what's sometimes called the maximum propagation times, between the clock and the Q. And after that time has passed, there's some propagation time from here to here, then back around. And then we need to wait some additional time, which is the setup time, while the data sets up here on D, before we can hit the clock again. And so that says that the clock period has to be more than the sum of the propagation times of the flip-flop and the combinational logic, plus the setup time. And then finally, we talked a little bit about clock skew, and clock skew just kind of makes everything worse. If it's possible that this clock and this clock are not going to be hit at exactly the same time, we have to add a little bit of extra margin for the clock skew. And so these two relationships which we had before, all you need to do to understand how the clock skew makes them harder to meet is to put them up there and say, which side of the inequality should I put the clock skew on in order to make the inequality more difficult to meet? And the answer here is that you add the clock skew on the left-hand side, saying that we have to ensure that the contamination delays are greater than a number which is bigger than it used to be because of clock skew. Yeah?
What does the squiggly line represent?
The squiggly line represents my attempt to draw the fact that this path is a different length than that path. Although, if you looked at it and measured it, it may actually turn out that they're the same length. But what I'm trying to say is that here's the clock coming into the system, and for one reason or the other, the clocks don't hit these 2 points at exactly the same time. And I've unwrapped the feedback loop here to show clock goes clock to Q through the combinational logic over here, and then either the setup or the hold for the data over here. And so the skew makes this inequality a little bit worse, and it does for this one as well. The clock period needs to be a little bit greater than it used to be because we have to take into account the skew. And this is a measure of the absolute sort of worst case difference. This is always going to be a positive number between different clocks in the system. And so if you have a nanosecond or something like that, you would put that in here to indicate the amount of clock skew that was in the system. But anyway, that's all by way of review. And now we're into the period of time when the projector blinks a little bit, and then it warms up and does better. The trouble with these setup and hold times is that we can't really guarantee that the system is going to obey them all of the time. In particular, here's our finite state machine. And we know that we may run into trouble if we feed it an input here that after it propagates through the combinational logic here may affect this data during the setup and hold time. And why is that the case? Well, these inputs are coming from the real world, from the outside. They're the keyboard keys that I'm going to type. They're the network packets that are coming in over the Ethernet or what have you. And we don't really have control of the relationship between the clock that's clocking the synchronous system here and the exact time of arrival of events from the outside world. And so if our finite state machine, you remember we did the example of the Coke machine the other day, if the nerd who comes up to the Coke machine presses the Coke button, the nerd is not going to sit there with a stethoscope or any other kind of scope and observe what the clock is of the system and push the Coke button just at the right time so he does not violate the setup and hold times of the flip-flop. It's possible that he's going to try to affect an input here and that will propagate through here and come in here just at the wrong time, just when the clock is going off. In other words, inside of the window between the sample and between the setup and the hold time. And so what are we going to do to fix that? Well, we talked before about adding flip-flops to the output of the system to get rid of glitches here and to get rid of hazards on the output. It turns out that one of the ways that you fix problems with an input here causing a change here during the setup and hold time is you put another register on the input. And here's the idea. I know from the previous diagram, the unwrapped loop, that if I set up a chain of a register and combinational logic and another register, that I can go ahead and clock these all at the same time and I'll obey the timing constraints. So if I have a problem with the timing constraints on this wire being bad, I'll just put a flip-flop there, and since I clock this one and this one at the same time, when the clock goes off on both of these, the amount of time it'll take the data to get here will be the same, and so therefore I will meet the setup and hold times going into here. And the same way going out to this output register over here. I'm clocking all three of these guys at exactly the same time. They're all in sync with each other, plus or minus the clock skew, but we saw how to deal with that before. So this sounds great, except for one thing. What is wrong with this picture? Have I really solved the problem of this input changing asynchronously with respect to the clock? Have I really solved it?
You just backed it up a step.
I just backed it up a step. That's right. I've just passed the buck to this flip-flop right here, and it may still be the case that the input here will change on this D input during the setup and hold time of the flip-flop with respect to this clock. This clock here is sitting there running at some frequency all on its own, and the input can come at any time. Now, I've solved it a little bit. Here's what I've made better than it used to be. I've at least simplified the problem. I've made what is wrong with this thing kind of stick out like a sore thumb now, because it's not kind of hidden behind a layer of logic on the input here. You remember that this logic here, unless I'm very careful, could have hazards in it. It could be the case that if I make a change here, this guy here is going to go through all kinds of glitches between the contamination delay and the propagation delay of this combinational logic right here. And it may be the case not only that we violate the setup and hold times here, but that we ask this guy to take a picture of data that is crazy, that is wrong, because this data here will be in flux during that time and may have a value that is neither appropriate for the old value of the input or the new one. Now we're making it a little bit better. We're saying, okay, this data here, if this flip-flop somehow miraculously does its job, will at least be clean, and so we don't have to worry about the hazards inside of here, but we still have the problem that this guy here itself may be asked to sample the input during the setup and hold time. But at least it's only sampling the input. It's not sampling a possibly hazardous combinational function of the input. So we've made it a little better, but not much better. So the question is, what do these things actually do? So let's take a look at the simplest case of all. We're going to use a 1-bit flip-flop, and we're going to have a clock on the bottom over there, and we're going to have a D input on the left, and we're going to look at what actually happens if that D input is changing near the time that the clock goes from low to high. So over here on the left, you'll see the D input. I don't know if you can see it well from the back. The D input goes up a little bit before the clock goes from low to high. And as a result, what should we expect to happen? Well, it's going to try to snap a picture of this thing when the D is high. And so what we kind of want this thing to do is whatever Q was before, we want it to go high and to store a high value because it's sampling D when it's high. Now, what if D comes a little bit after the clock, like this case on the right? In this case, the clock went from low to high before D went from low to high, and so we want Q to give us the answer that D was low. And so if we step back a minute and ask ourselves, what is this thing really trying to do? The answer is it's trying to arbitrate between the clock input and the D input. Which one came first? Did the clock go from low to high first, or did the D input go from low to high first? And where we're running into trouble, if we think about it, is when the D input is changing too close to when the clock input changes, and we're asking this thing to discern a race between these two edges, one on D and one on clock, that becomes, to use a word that we've heard a lot in the times now, too close to call, right? What if it's too close to call? What if it's during the setup and hold time? What is this thing going to do? But it's important to understand that this function of taking a sample of a potentially changing input is exactly the same as trying to decide which came first, D or clock. Okay? Now, well, what happens? The specification that you get from the book says absolutely nothing. It just says if this D input is changing during the setup and hold time around the edge of the clock, all bets are off. Okay? It's not that the thing's going to blow up, but it doesn't give any guarantee at all about what it's going to do. Well, it turns out that this problem is not very new, and it didn't start out in the digital age. It actually started, or was talked about back in the 1300s by this philosopher named Buridan. And I won't go ahead and read all this stuff, but the story is that you've got this donkey, I'll call it, and he's sitting here, and you put two bales of hay, one on one side and one on the other, that are equidistant from the donkey. How does the donkey decide which one to go to? The donkey feels the, smells the smell of the hay from this side, smells the smell of the hay from the other side, and in its little brain, it's kind of weighing the scales, right? Which is more and which is more. What does it do? And what Buridan hypothesized was that the donkey might starve to death. Sitting there in indecision, sort of like trying to decide on a president, right? Nothing will ever happen. And this was an incredibly important thing because it turned out that even though he was just a philosopher, in fact, he stumbled upon something which is, and I say that just jokingly, he stumbled upon something which is incredibly deep, okay? It's a deep thing that the closer the race is, the longer it takes to decide who won. Again, something we've seen recently, okay? And it seems obvious, but it turns out that there are actually rules in physics saying that this is true, okay? And, you can invent all kinds of things to try to get the donkey here to go one way or the other. You can invent a wind, let's say, and he gets to smell the one that's on this side because the wind is going from here to here, and so he decides to go to the left. But, if that's true, let's just start the donkey off a little bit closer to the other bale of hay here. Okay, this is the only picture that I could find on the web was these kind of chives. But just think of it as hay, okay? What if we started the donkey closer to the other bale here, right? And there was a wind. Well, somewhere there will be an equilibrium point, again, where the attraction of the two is exactly the same in the little mind of the donkey. And then you say, okay, well, what we're going to do is we're going to wait so many weeks, and if the donkey hasn't made up his mind, we're going to give him a kick to one side or the other, right? But what happens in that case if just before we're about to give him a kick, the donkey says, oh, I've made up my mind? What do we need to do in that case? We need to decide which came first, our little timer that says the donkey's run out of time and it's time to give him a kick, or the donkey making up his mind. And that problem is an arbitration problem. Which came first, the donkey making up his mind or the donkey running out of time? And so, in fact, there is, in general, no answer to this. And it is possible, in fact, for a donkey to starve to death trying to, well, not a real donkey, but, you know. Now, a real donkey, of course, has never starved to death, as far as we know, going in between two bales of hay. But theoretically, it is possible. And we're going to talk about exactly what the mathematics of that are like. Another example is a game show. Here we have two contestants, A and B. And you guys have seen this before. They each have a button to press, and an arbiter needs to decide which one pressed the button first. This problem is exactly the same. In fact, you could go ahead and hook up A to the clock input of a flip-flop and B to the D input of a flip-flop, and the flip-flop would have to make up its mind. Except if both of the buttons are pressed down almost simultaneously, you might violate the setup and hold times of the flip-flop. And so far, you guys don't know what's going to happen. Well, it turns out that a edge-triggered flip-flop is a more sophisticated version of an arbiter than we actually need to build in order to solve the problem. And so I'm going to take this one notch down and go back to our fundamental mode state machines. If you remember, we talked about D-latches and set-reset flip-flops. Well, this is actually a version of a set-reset flip-flop which is used to decide which one wins. And so just trace through a circuit with me here for just a second. This is what you might use if you're trying to decide a game show. If A presses a button and A goes from 0 to 1 before B goes from 0 to 1, then what takes place? Well, let's say both of them are low to begin with. These are both low. Well, if these are both low, what's the output of the AND of a low thing and anything else? Low. Okay, so these are both low, and they both cross around like this. Beautiful circuit with symmetry. And they go to an inversion, which is high. So both of these sort of have high inputs right at the input to the AND here. Now let's say A goes high first. A goes high first, and both of these inputs to this AND are high. What happens? It says, okay, A wins. And then that high value propagates around here, comes to this bubble over here, which inverts it, and then the input to the AND is low. And therefore, will it listen to B after that? No. So A gets to basically shut off the gate for B and say, I win. B, of course, it's a symmetric circuit, so if B happens first, B gets to shut off the gate for A, and B wins. Sounds great. What happens if both of these guys go off at the same time? Well, let's draw the circuit here. Okay, so we said we're going to start out with both of these things being low. Low, and the output from here we said was going to be low. This was going to be low, and this was going to be low over here. Okay, and this gets inverted on the inside to become high. Okay, now both of them are going to go high at the same time. And just taking an extremely crude model of time, where time is just going to go in steps with the letters on the board, let's say they both go high at the same time. Okay, what's the output of both of these AND gates if both of these go high at the same time?
1 instantly and then 0 instantly and then 1.
Ah, yes. So both of these go high, comes around here, both of these go high. Then what happens?
They both go low.
Then these highs go through the inversion, which causes the gates to go low. And that goes around, and that goes around, and without too much, okay? And it begins to sound like the court decisions coming out of Florida, right? As they go around and around and around and around, making up their mind. So we begin to see the possibility of a kind of behavior here which is not exactly like the donkey in between two bales of hay where he just kind of sits there and says, I can't make up my mind, right? But rather he kind of sort of goes to one side, goes to the other side, goes to one side, goes to the other side. And this is the other kind of indecision that circuits like this can make, where in fact they oscillate. They sit there and they keep... Now notice it's not really making up its mind in either of the cases. It keeps flipping back and forth between no one won and everybody won, and no one won and everybody won, and no one won and everybody won. And the ones and the zeros are chasing each other around in this loop, okay, which is just a weird thing, but it can happen. Okay? And circuits like this, in fact, if you hook an oscilloscope up to them, can oscillate. Okay. Now, let's take another look at this circuit. If both of the inputs to a circuit like this are high, and I've moved the bubbles here from the input part of the gates, I've kind of pushed them around to the output part of the gates. But you all agree I haven't changed the circuit at all. If both inputs are high, this circuit is really the same as two inversions hooked together in a loop. Because if one input of a NAND gate like this is high, then the input comes in and is inverted going to the output. So we have two inversions going around in the loop, and the inverse of an inverse is just the same thing, and you end up with a logic circuit that basically just has feedback like this. And this should look very familiar because it's just like the logic circuit that we talked about in the D latch, where it used a circuit with positive feedback like this to latch on to either a 0 or a 1. This circuit, when the inputs are both high, is desperately trying to latch on to either a 0 or a 1. The problem is that we're setting it up in the middle, and it doesn't know which one to go to, whether to hold on to a 0 or a 1. And so there's sort of two different circumstances that a circuit like this can get stuck in. One of them is called static metastability, and the other one is called dynamic metastability. But the important thing is that you understand this word metastability to begin with, and what it means is that it's not stable. It's not holding on to a 1 or holding on to a 0, but it is metastable, and that means that it is indeterminate, somewhere in the middle, trying to make up its mind. Now, it turns out that a logic circuit like this has what we call positive gain. In other words, if this is the voltage on the input, on the x-axis here, and the y-axis is the voltage on the output, then as the voltage on the input goes from a low value all the way up to a high value over here, the voltage on the output has a curve that looks sort of like this S-shaped thing over here. And this is actually your first introduction to the idea of gain inside of circuits. And what the gain means is that instead of this straight line over here, which would be V out equals V in other words, the output of a gate like this is equal to the input of the gate, what the circuit does is it says, look, I want to make sure that in order to hold on to this output, that I have some amplification of the signal. And so the slope of the line, this dark line here, which is the transfer curve of a circuit like this, in fact has a slope greater than 1. The output is an amplified version of the input. And since the slope is greater than 1, it does what everybody who's played around with an audio amplifier knows. If you turn the gain up too high, it clips the output, right? And so within this range, it's a nice gain more than 1, but past a certain point, it saturates, and that's as high as it can go. And past this point on the left-hand side, it saturates, and that's as low as it can go. And it turns out that this is a wonderful thing, and it allows the device, when you hook it in feedback, to hold on to the value very well. And we'll talk about noise in a future lecture and how a circuit like this can reject noise. But for now, if you remember the idea of how a dynamic RAM works, how it reads the value and amplifies it and then writes it back. If you remember the idea of the bathtub with the leak in it, right? We're going to look at the bathtub and see if it's high or low. And then if it's high, we're going to add more water to the tub, right, to fill it up the rest of the way. This function is doing the same thing. It's amplifying the output as it comes back around here and sending it back out in an amplified version. Now, when I hook a circuit together in a feedback loop like this, what you will notice is that there are 3 places where the lines cross. This straight line over here is the equation of the wire, where the output voltage is equal to the input voltage. And the S-shaped curve is the equation of this logic buffer, which does nothing more than take the input and produce it on the output with some amplification. And you'll notice that they cross in 3 places. This place over here is what's called the stable high state. In other words, this circuit is capable of latching a high value right here. And if, for whatever reason, because of leakage or noise or whatever, the voltage begins to decrease a little bit, the amplification of the buffer will push it back up. In a similar way, this state down here, which is called the low state, the stable low state, works the same way. It holds on to a low voltage value, and if there's a little bit of drift in that value because of noise or or some leakage, it'll push it back down again. But notice that the curve also crosses in this third place right here. And this is what's called the metastable location. And here's what goes on here. Right here in the middle, V out equals V in. Now, V out equals V in, except that there's amplification in that triangle, which means that if a little bit of noise comes by and V out equals a little bit more than this middle point, then the amplification will make it be even further, even more positive, and more and more and more until it finally drives to here. On the other hand, if it's sitting right here and it drifts negative a little bit, the amplification will drive it the rest of the way down to the bottom. Now, if you don't like circuits, let's think about the donkey again. The donkey is sitting in the middle between these two succulent bales of hay, right? A little bit to the left, a little bit to the right, right? If for some reason you go up to the donkey and just push him a little bit to the left, what happens? The bale of the hay on the left now is stronger than the bale of the hay on the right, right? So he drifts even more to the left, right? And the closer he gets to the left, the more the attraction of the left is greater than the attraction on the right. So he moves even faster to the left, right? And you would expect that as a function of time, he might start out kind of really slowly going off to the left, but the stronger it got, the faster he would move towards it until he's sitting there eating it. The same kind of thing might happen over on the right. And again, there are two stable places with the donkey eating a bale of hay on the left or a bale of hay on the right, and there's a metastable place where the donkey is in the middle and can't make up his mind one way or the other. And this works exactly the same way. Now, for those of you that are somewhat familiar with circuits, and we're going to get a little bit more into this in the future, you can describe the dynamics, how this circuit evolves with time in terms of a capacitance and a resistance, and that it takes time for this circuit here to charge up. All that that's really saying is that the donkey has some mass and it takes him time to move over to the left-hand side or time to move over to the right-hand side. I like to give many different physical examples of this phenomena so that no matter what sort of background you have, you can understand what it's like.
Think of a bag standing on its end.
Yes. Oh, so here is a inverted pendulum, which is yet another example. And so we can think of a pen like this standing on its point, right? And which way is it going to fall? Is it going to fall to the right, or is it going to fall to the left? And the answer is, if it's right here in the middle, supposedly it can stay there for a very long time because the forces are exactly balanced, and then it can eventually fall one way or the other. And if you think about the potential energy of the mass sitting on top of the stick here, it is the greatest when it's straight up and down, and it's the least when it's leaned over to the right or it's leaned over to the left. So in fact, there is a hill here in energy that has a crest right here at the top. And I can think about the state of the system as a little ball sitting on top of this hill. And how long can the ball stay at the top of the hill? Let's say the hill is a perfectly smooth thing and the ball is a perfectly smooth thing. Now I know if I start the ball here over on the right, it'll start out slowly, but eventually it'll go faster and faster and end up in this state on the right. And if I start it out on the left, it will do the same thing going on the left-hand side. But theoretically, I could start it out exactly in the middle of the hill, and it might balance there forever, just like the donkey in the middle, or perhaps the flip-flop. Well, let's take a look at exactly what the physicists say about this thing. There's a certain principle called the Heisenberg uncertainty principle. Now let's see, do we have any physicists here? Anybody that actually knows this stuff? Okay, so what does this basically say? In order to actually know the state of a pendulum like this that's standing up, we actually need to know two things. We need to know both its position and its speed when it's up at the top there. And it turns out that the Heisenberg uncertainty principle says that we cannot know those two things sufficiently accurately to place a upside-down pen like this in a position to balance longer than a certain length of time. And I think for a typical pen, it's like 10 seconds or so. Okay? And what typically happens in the course at MIT is that the students who have taken physics courses all raise their hands and say, I know that a pen can't stay up for more than 10 seconds. So therefore, all the stuff you're telling me now is false, and I know that this metastable state cannot last for very long. The donkey will not starve because Heisenberg says so. Okay? But it turns out that Heisenberg does not say so. What Heisenberg says is I cannot know the position, or actually the position and the momentum, which is another way of saying I can't know both the speed and the position of the pen sufficiently accurately to guarantee that it will stay up for more than approximately 10 seconds or so. Okay? In other words, I can't, as somebody on the outside, say, I promise you I'm going to place this pen with my fingers here, even if my fingers were perfect, in such a way that when I let go of it, it'll stay up for more than 10 seconds. I can't guarantee that. On the other hand, it doesn't say, Heisenberg does not say, that it might not stay up for 3 years, or for 10 years, or for 1,000,000 years. Okay? Nothing in the uncertainty principle says that a metastable state may not, in fact, last forever. And so when you come across this thing, and it's a typical sort of things that's taught in physics courses when they talk about that, is how long can a pen stay up? They talk about how long can you guarantee a pen will stay up, not how long might it stay up. So, okay. So we're learning a little bit about this arbitration problem. The arbitration problem seems to be a problem where we're trying to build a device that is going to give us a correct answer as to who won, who came first, either contestant A or contestant B. It's measuring the time between A and the time between B when they went off. But you know, when you see that it becomes hard to decide if the time difference is small, if the time difference is near zero, another thing that you may be tempted to do is to say, look, I'm willing, if the race is really close, to say I don't care what the answer is, as long as all the votes are. Oh no, wait, that's a different thing. I am willing. This is the perfect time to be teaching this because it's absolutely true. No, one of the things that you might say is that I expect that the inaccuracies in the button mechanism, the inaccuracy in the time delay through the circuit, will make the process fundamentally impossible to decide fairly if the time is within a certain margin. The same as with the votes, right? Certainly the race is within the margin of error, right? Well, you may be willing to say, I'm willing to relax the constraints on building an arbiter by saying it's okay if I say the following thing. If the time difference is less than a certain margin, t sub margin, then it's okay if the arbiter picks a random result. Sounds good, right? Who's going to be able to tell the difference? No one, right? Okay. Do you think that this solves the problem? In other words, if we tell the donkey, you know what? If you are having trouble deciding, it's okay if you flip a little coin in your little head and choose at random either the left bale of hay or the right bale of hay. You think that can solve the problem? In other words,
some cases we're going to be on the border of that particular.
That the coin might flip and land on its edge.
Or not.
Is it on the margin or not? Absolutely right, because we won't be able to tell whether or not we're within the gray zone or whether we should give a definite answer. So we insist the donkey be accurate if he's by a certain amount to the right of the midline, and be accurate if he's past a certain amount to the left of the midline. But if he's in the middle, we allow him to come up with the wrong answer, and that doesn't even make it easier to do. And so that's an amazing thing, because it turns out that it is impossible to build this thing called the perfect arbiter. Here's the definition, the formal definition. First of all, we have a constant called t sub margin, which is this amount of accuracy that we demand. And furthermore, we have a finite thing called t sub pd, which is the propagation delay of the arbiter. And we say that if t sub a minus t sub b, the time of arrival of event A and B, are greater than t sub margin, the absolute value of that. So if one is before the other more than t sub margin, we insist that the output be correct. It's okay for it to give any output if we're less than or equal to the margin, but we also insist that the arbitration take a finite amount of time, t sub pd. And guess what? It turns out that as far as we know, it is impossible to build an arbiter like this. Okay? which is an amazing fact. Now, it turns out that, as I showed you before on the board, we can have ones and zeros chase each other around the room, around the loop over there. And you can show that in a circuit. If you have two R's and two C's, it turns out that a circuit like this can oscillate, and if you were to put a scope, which we can't do in this class, on this node here or on that node there, you'd actually see the waveform jumping up and down and up and down and up and down before it made up its mind. I'm going to skip over that part because that's the demo circuit from MIT. Here's another question. Can we build an arbiter that looks like this? An arbiter takes in A and B, and it tries to decide which came first, A or B. And it gives its answer out over here, and it also has a flag saying when it's made up its mind. Well, obviously the answer is yes, but the question is, why can we build this thing? And if you think back to the example of the donkey in the middle or the pen that's standing up like this, the answer is that it's obviously easy. You just wait until the pen hits the ground one way or the other, or the donkey moves to one bale of hay or the other. And as soon as you see that that has taken place, you say, now it's done, and you raise the flag here. So it is possible to build this asynchronous arbiter, the one that has no fixed time limit on how long it should take to make up its mind, but it's not possible to build one that has to give this done answer within a finite amount of time. Okay. How do we, in practice, actually take care of this issue? Well, I just showed you that we're going to put a flip-flop in front of the FSM that's clocked off of the same thing. What we're going to do is we're going to say the clock goes off here. If this input happens to obey the setup and hold time, then everything's fine. We have no reason to think that there's going to be trouble in the first place. But if the race is too close to call and the input over here violates the setup and hold times of this thing, then we know that this device here may enter the metastable state of sitting there in the middle saying, should it be a 0 or should it be a 1? Or it may oscillate, saying 0, 1, 0, 1, 0, 1, 0, 1. But we also know that like the donkey, like the pen standing on the top here, the circuit will eventually end up in one or the other, although we can't bound how much time that's going to be. It will be attracted to one of the two stable things of the 0 or the 1. So what do we think about the probability that this circuit is going to mess up? Well, the answer is it depends how fast the clock is. Because once the clock goes off, if we waited around for a long time before we supply the clock again, in other words, before we expect this FSM to make use of the answer that comes out of this thing, we will give time for the donkey, for the flip-flop here, to make up its mind, for those ones and those zeros to resolve. Now let's talk about how the ones and the zeros might resolve over here. Why would this ever end up in a nice state, either high here and low here, which means that this top guy won, or low and high, which means that the bottom one won? Why would that ever happen in a circuit like this?
One of the electricity going around in one path may be a little bit slower than one of the other.
Right. It may be the case that the time delays in the circuit are not exactly the same. And actually, again, think about this. If both of these are high, and these are staying high for the rest of time, right? After we press the button here both at the same time, it may in fact be the case that the high values as they propagate around are a little bit slower or a little bit faster than the lows that are propagating around. And another way of thinking about the signal here is that this looks like this square wave here, right? And this one does too. It may be the case that this edge gets delayed a little bit and moves out towards here, and the pulses begin to get a little bit wider. Or it may be the case that these get a little bit wider. But one way or the other, this thing will tend after a while to die down. It'll ring and ring and ring, flip-flopping back and forth and back and forth. But eventually, either the highs will grow or the lows will grow. In fact, you may think that it's impossible, since it's always impossible for two real values in the real world to have exactly the same value. The propagation times of the rising edge and the falling edge of this thing cannot always be exactly the same. And so it will always be the case that this will tend to extinguish the oscillation that goes on here, and it'll end up being a value that's high or a value that's low, like that. Or maybe the other way, okay? So even in the dynamic case, the oscillation will die down. Phil, why don't you stand up? We're going to use you for a demo. Why don't you pretend that, once again, you're an MIT student.
Okay.
And you're going to start over there, and you're going to walk towards me. And you know how MIT students are when they walk down the hall. You know, they are not thinking very much about what they're doing, and they tend to kind of do dumb things, right? We're reading the book. And the two of us are walking towards each other, and we bump into each other, and the hall is only so wide.
Okay.
And so the two of us decide to step over here to get past each other. And then the two of us decide to step over there to get past each other, and then over and over again. And you see this at MIT now and then, right? And the question is, how long can this go on? And the answer is, this is exactly the same as the ones and the zeros chasing each other around the loop here. Okay? In that this circuit is trying to decide which one will get to squeeze in front of the other one and shut the other one down. And finally, one of us will be a little bit slower going one way or the other way, and we'll end up passing, perhaps bumping into each other like this, never even actually having looked up from our books to see each other. Okay, thanks. Okay, but that gives you an idea of how the ones might win out over the zeros, or the zeros over the ones. And of course, it's not the case, however, that that says that it's a way of guaranteeing that we'll get out. We may be stuck there forever. It all has to do with the exact time that we hit each other like this, exactly where we were with respect to each other. And it is theoretically possible for a circuit like this to oscillate forever if we happen to start it out in just the state where it's balanced between going one way and going the other way in a dynamic sense. Okay?
Does this have anything to do with the one that wins out in the end isn't necessarily the one that came the slightest bit ahead of time? Is it?
That's absolutely right. And in general, you might think that the more A leads B, the more the circuit should say A wins. But as soon as they come very close to each other, things begin to depend on all kinds of stuff. The temperature of the room, whether there's somebody that turns on a light, whether there's a butterfly on the other side of a world that flaps its wings, you know, all sorts of things like that. No, it's absolutely true. That the closer they get to each other, the more exquisitely sensitive the circuit becomes to noise. Because, you know, again, the pendulum that starts off like this, right, at the beginning, if it's off by much, it has a lot to do with where I started it. But if I started out right in the middle and it gets, you know, where it stands there for 10 seconds or more, it has very little to do with what I did, and has a lot to do with which way the wind was going here, and whether the, you know, molecules of the air are bouncing on the left-hand side or bouncing on the right-hand side more as time goes on.
But it still seems to me, if I set up this thing in a finite number of times, the probability you'll set up in the right state is 0. You have to try an infinite amount of time to get there.
Okay, so you're absolutely right, okay? But let's get to there by, first of all, asking ourselves the question, how do we in practice solve this issue? Now, in practice, I don't worry about walking down the hall and getting stuck forever, right? It turns out in practice, we don't have to really worry about this with a circuit like this if we leave enough time for the situation to resolve. It may be the case, and you've seen people do this on the sidewalk, right? Or at least in the movies on television, you see people do it on the sidewalk. But we always manage to get past each other. So if we leave enough time from one clock to the next with a circuit like this, we can be guaranteed that this thing, well, we can't be guaranteed, but we can think that this thing will have enough time to resolve the issue before we clock the next one. So let's actually take a look at the mathematics that have to do with how fast this circuit will evolve over time. Now, I know that many of you do not have a background in circuits, but I think I can teach you enough during the time now so that you'll understand how this thing works. Basically, what's going on here is we have this amplifier A, and we have a resistor and a capacitor which act to slow down or give some momentum to the circuit. The same way we have a donkey with some mass to it, okay? And it is attracted to one bale of hay or the other with an attraction that's proportional to how close it is to the bale of hay. If it's in the middle, it doesn't know what to do, but the closer it gets to one side, the more it's attracted towards there. Now, it has some mass to it, So it doesn't instantly go over there. It takes it some time, but you might imagine that it walks faster and faster as it goes towards the end. And so if I were to draw a set of curves over here for what the evolution of either a donkey or a pendulum or two nerds or whatever you want versus time might be, where this is the low value and this is a high value over here, if I started them out in the middle, what I'm claiming is that they may stay there forever as time goes by. But if I started them out, let's say, over here, then chances are it'll become high, but it will start out sort of at this speed, and then the closer it gets to going high, the faster it goes like that. And if I started out over there in exactly this symmetric case, it'll go towards low like that. In other words, as time goes by, the closer we get to being either low or high, the higher this slope is, the faster the slope is towards getting there. Okay? Now what might happen here? Well, I started this out a little wrong. This should actually have some slope to it at the beginning. Can't really draw very well. Okay? Over here we would expect the initial slope to be less than this is here. So think of this slope as being half of that slope. Okay? But as soon as we get down to here, this curve for the rest of the way will be identical to this curve that we've just drawn here, like so. And in the same sense, if we start out over here, the slope's going to be less, and then when we get to over here, this curve is just a copy of this curve here. Because after all, this is our state, and once we're in this state, being this close to the high, we do the same thing, but just shift it in time. And then over here, if we did that, that would be even less of a slope, and then when we get to this point, this curve is the same as that curve with time. Okay? And then if we're half of that, okay, now I'll start to get a little loose here. Now I draw. That'll go like that, and then even closer, a curve perhaps like this.
What are your axes?
So the x-axis is time, and the y-axis could be anything. Let's say that it's voltage, V, between a high voltage and a low voltage. And in the middle is the balance point, the metastable point. So here we're looking at how we evolve with time. The pendulum going to the left or the right would work the same way. The donkey going to one bale of hay or the other bale of hay would work the same way. And now we begin to understand that the closer we start out to the middle, let's say we start out this close, the longer it's going to take us to make up our minds whether we're high or we're low. If we start out further away from the middle, we can find out fast who won, whether we were closer to one side or closer to the other side. And that has to do with who won in time, or whether we started out to the left or the right of the balance point in the middle. The idea is the same.
Just a quick question.
Yeah.
Statistically, is each voltage interval as likely to occur as another?
That's a wonderful question.
So if that was broken into 10 intervals, would the middle 10 be just as likely?
That's a great question. So in fact, what we're going to assume is that our digital signals sort of look like this. Here's a high, here's a low, and here's a time when they transition from high to low. During this time, when it's low, there's no chance that it's going to be anywhere in the middle. It's going to be down on the bottom. During this time, there's no chance because it's going to be up on the top. And during this time, statistically, since it's making an even change from one to the other, we're going to assume that the chance that it's anywhere along this line is equal.
So it is an even.
We're going to assume that during this fraction of the cycle, it's equally likely. Okay.
That fraction of the cycle is only a small fraction.
It'll be a small fraction of the cycle, yeah. Okay, it turns out that those curves that I just drew there are what are called exponential curves, okay? They have a characteristic which exponential curves have, that the derivative of the function is equal to the function, okay, times some constant. In other words, the slope of the line here is equal to some constant times what the y value is. In other words, the more we get towards a higher value of y, the higher the slope gets in a linear way. Okay? And here, let's assume this is 0 here. The more negative we get, the more negative the slope is, the faster we go down. It's exactly the same as the donkey in between the two bales of hay. The closer he is to one bale of hay, the faster he moves towards that side, times some constant. And
Not in a linear way, exponential.
well, the slope is a linear function of how close you are to one side or the other. So this slope here is equal to k times whatever the y value is. Okay? Okay, all right. So in fact, what we have, I've just showed you this one, is a function that looks like this. We have an exponent of the constant e, which is 2.71828, times t over tau. Now t is time, and tau is what's called the time constant of the circuit. If t is big, it means that we take a relatively modest, slow way to get to one side or the other. It's still the case that the slope is proportional to how close we are to one side or the other, but that proportional constant is small. The donkey is very heavy, and he's not very hungry. Okay, so tau is big. Okay, so it takes a lot of time for t over tau to get to be a big number. But the curve is exponentially increasing towards the left or the right-hand side. On the other hand, if the donkey is lightweight and very hungry, tau will be small and this will be fast. And the Vn of t is equal to Vn of 0, where we start out, times this exponential e to the t over tau. And it has to do with the circuit gain here, 1 over a, but for right now, we can just think about that as how much amplification is in the circuit as it goes around the loop. And when you work out the math of this, what you discover is that the probability that you will stay in a metastable state for a time t is equal to e to the minus t over tau divided by a. And what that means is that I'm going to ask the following question. Let's say that I decide that I want all metastability to be over by time t here. Okay, am I using a capital T? No, a small t there. In other words, I want all of the metastability to be done by this time. Well, that's true for this curve. It's true for this curve. It's not true for that curve. And in fact, if I back up, if I say, what is V in when I start out? V in of 0 is the time here that I start. It's true that between this time and, if I back this out here, this time here, for all voltages inside of this range here, those will take longer. Okay? So that's all that this is saying here, is that Vn of 0 is e to the minus t over tau going backwards from here. And from that, I can get, again, the question that I forgot who it was that asked it, that you asked, which is, what is the probability that I will be metastable past a certain time? Well, if the voltage was going up and down and up and down and up and down, the nerd was sitting there pushing the Coke button over and over and over again, so that this voltage was always in transition up and down, then the probability that it's going to take more than this time is this length divided by that length, because it's equally likely to be in any of the places here on the y-axis. Okay? Therefore, the chance that it falls inside of this range is just this range divided by that range. Does that make sense? Okay, good. So the chance that a system will be metastable past time t is just this distance divided by that distance. Now, you have to take into account the fact that it will only be in transition a fraction of the time. And so that's what we take into account here. The probability that you are metastable after time t is equal to, first of all, the probability that you're in transition at all. So if 80% of the time you're not in transition, then only 20% of the time do you have a probability of being metastable. So that's why you multiply by the probability that you're in transition. And then you also have this a e to the t over tau, which has to do with what the probability is based on exactly how big this part of the curve is. Okay? And so, in summary, what you get is the probability that you are metastable is p transition divided by this amplification A of the feedback times e to the minus t over tau, because it's on the bottom over here. So e to the minus t over tau. What does that look like? Anybody know what that looks like? So some constant k e to the minus t over tau.
That's according to the x-axis.
So it kind of looks like that. Okay, it's getting closer and closer and closer to 0. Okay, it has a wonderful characteristic that if it was at a certain value here after 1 second, let's say this is f of t. This is f of 1. Okay, if that was that value, what is f of 2? If it took 1 second to get down here, where is it after 2 seconds? It's going to be half of that, right? And then f of 3, half of that, and half of that, and half of that. So it exponentially goes down with every, so this is f of 1 over 2. Then after 3 seconds, where's it going to be? F of 1 over 4. So it's sort of geometrically decreasing every second of time that goes by. Now you guys all know how fast a geometric series gets big. Something that geometrically decreases gets small very, very fast. So every second that goes by, we cut down again the probability that it's metastable. And so that goes down very, very fast. And here's this function right over here. And it's possible to invert this function over here to put it in terms of time. And the question here is, how long will we have to wait until the probability goes down to a certain value, p of metastable? I won't go through the math here. It's actually not as hard as it looks. You guys can go through it afterwards. But what I will show you here is what the results are of that. So let's assume that we have a system that is being clocked at 100 megahertz. The flip-flop is being clocked 100 million times per second. That means that the time we have between cycles is 10 nanoseconds. And let's say that the waveform is spending 10% of its time in transition, and the gain of the amplification in the flip-flop is 10, A is 10. And we assume that the time constants inside the circuit are around 1 billionth of a second, 1 nanosecond. And so this is sort of typical values for what you would find inside of a finite state machine inside of a processor chip. And let's say that we decided that we wanted the chance that you're metastable to be the case that even though it's doing 100 million arbitrations per second, that I only want one of them to go bad every year, that I'm willing for my system to freeze up once per year, because after all, it's running Windows and it freezes up once a day anyway, right? So once a year is a good number to use. Well, the probability that any transition is metastable is going to be this 1 year, which is around pi times 10 to the 7th seconds, it turns out. This doesn't mean anything. This is a big joke. Okay, this is a Jerry Sussman joke. That 1 year turns out to be around pi times 10 to the 7th seconds. Okay, it didn't need to be. It just happens to be. And it's not really pi. It's 3 something. Okay, but if you need to remember how many seconds are in a year, this is roughly right. Okay, 100 megahertz is 10 to the 8th cycles per second. Okay, so you multiply these by each other and you get the probability of the metastability is you want it for any given cycle, if it's going to fail once a year, to be roughly pi times 10 to the minus 16 is the probability that any given cycle is going to go bad. Crank through all of the numbers and you say, how long do we have to wait for a flip-flop to decide its value if we want the probability that it will still have not made up its mind to be pi times 10 to the minus 16th? And the answer is around 31 nanoseconds. That's 31 billionths of a second. So if we feed this asynchronous input to the flip-flop, and we do it 100 million times a second, and we're willing for it to not have come up with the answer once a year, then if we only wait 31 billionths of a second after we give it the problem, it will come up with the answer every time except once per year. And once per year, it'll take longer. Okay, yeah?
Where does this time come in since we're talking to every 10?
That's absolutely right. It seems that we're screwed, right? Because after all, we're clocking this thing so fast that this seems like a time that is longer. This may seem 31 billionths of a second, after all, is not very much time. Okay, even in dog years. But it is a tremendously long length of time in terms of a processor, for instance, that's going at 100 megahertz, or these days, one's going at a gigahertz. This is 31 clock cycles for a gigahertz processor that need to be wasted while idling away, waiting for the flip-flop to come up with the answer. And while we're waiting for it to settle down with the answer, we could be doing other work. So we're going to have to figure out some way to fix this. Well, just before we get off this thing, I just want to show you the power of these exponential decreases, because let's say we wanted it to only fail once every 10 years rather than once each year. If we were running Linux on the system, right? It doesn't fail more than once a year, so we want the system to not fail more than once a year. And so if we want to increase the probability, or excuse me, decrease the probability by a factor of 10, it turns out we only need to wait 33 nanoseconds instead of 31.
How fixed is the value of tau? Because that has a
tremendous effect on the system. That's absolutely right. So if this was 0.1, then this might become much less than that. It would be 3 point something nanoseconds as opposed to 33. But these are sort of typical values that are out there. Yep. And A is pretty much fixed too. Okay. Well, if we want to, we could wait even more than 33 billionths of a second. We could wait 100 billionths of a second, because after all, if we're going to wait for 33 clock cycles, we may as well wait for 100, because that's a long time too, but not that long. And it turns out when you work the numbers out, the probability that it will still be metastable after 100 billionths of a second is 10 to the minus 45.4. Or if you're running it at 100 megahertz, it's around one failure every 10 to the 30th years. So even Phil's software will not be hobbled by this thing. And just to give you an idea of how big a number 10 to the 30th years is, we have some great thing here. Age of man, 10 to the 7th, age of the earth, age of the universe, 10 to the 10th. So you can, to answer your question now, probabilistically reduce the chance that you will still be metastable to a tremendously low number. But you do have to wait some time. And the amount of time you need to wait, if we're going to wait for this long, and this, by the way, is the typical length of time that is used. If you talk to any digital engineer that's out there and you ask them how long do you wait for a metastable state to resolve itself between one state or the other, the answer is 100 billionths of a second. Okay, that's how long we wait.
But aiming at 10 to the minus 45th is completely excessive.
It's totally crazy. But it turns out that this is so that you have to wait 30 nanoseconds at least. So the idea is, well, if we're going to wait for that long, we may as well wait for 100.
What's the probability that a photon from space is going to hit our computer?
And zap it, right. That's also a very low number. And we're going to get into this thing.
Near as low as this.
It's probably not as low as this, right? And that is only one of many types of errors that could happen. And so, in fact, we're going to talk in a later lecture about all of the different effects that could happen to screw us up. And we're going to learn that, in fact, computers are not truly fail-safe things. Okay? That, in fact, they have a non-zero probability of failing at any given time.
That can't possibly be true.
Well, many students think so, but it's actually not true.
Is the 100 nanoseconds also used to cover other things that are going on?
No.
It's only for this purpose?
Right.
But this is only on the input side.
Only on asynchronous inputs. Okay. And so here's the way to think about this now. If you obey the setup and hold times, you can pretty much be sure that everything will work just fine, except if the photon comes in or some other bad thing happens. And we'll talk about the probability of that too.
In my short life, I've had a photon come in. I'll tell you about it later.
Okay, well. But if you're not going to obey the setup and hold time, here's what you can depend on. You can't depend on the flip-flop giving you the answer in the propagation time of the flip-flop, which is typically 2 nanoseconds. What will happen is if you violate the setup and hold time, it'll take longer to make up its mind, and the answer may be random. Okay? And it may take forever. But the chance that it'll take forever is very, very low. And in fact, the chance that it'll take more than 100 billionths of a second is so low that if we allow this much time to take for it to settle down one way or the other, we can pretty much be sure that it will have settled in one state or the other, and we don't need to worry about it. What?
Well, 10 to the 30 is a long time for one processor. But like the Study at Home project has collected at least like 10 to the
A little louder, please.
8 or 9. I guess that's still a lot.
10 to the 30 years, you know, even if you, like the age of the universe is 10 to the 10th year, so we have a factor of 10 to the 20 to play with here before we get to the age of the universe. Okay, so I think we're okay. Even if everybody had a processor and they're all going at the same time, I think that we're still cool.
The important thing is you can't run this on every flip flop, right? So there's still the question of you have to determine whether or not it's an asynchronous input, determine whether or not you put it into
Right.
this.
We are only going to do this, so let me actually, since it's not in the lecture, I don't think, let me go ahead and skip to a future lecture and tell you how we're going to solve this problem.
The problem of deciding whether or not to delay or what problem?
Of how to synchronize these things. Sure, you don't want to do it on every, this is actually in a later lecture, but let's talk about it now, okay? Here's your FSM, combination logic. And let's say that we're going to clock this at 1 gigahertz. Okay, this is on the inside of the Pentium 4 or something, right? It's actually 1.5 now. But. Okay, this is, let's say, 1 nanosecond in between pulses. And despite their attempts to make it not so, there are actually real-world inputs to the Pentium 4. Okay? How are we going to deal with it? I'm telling you that if there's a register here, and we clock this guy with the same clock as here, we have to wait 100 clock cycles before we can make use of this output. So what are we going to do? This doesn't work, right? Because this will clock, you know, here's my Coke button, right? Give me a Coke, right? Because everybody knows the Pentium 4 is going to end up on the inside of a Coke machine, you know, pretty soon anyway. Okay, give me a Coke. Uh-oh, I got the wrong answer. I'm putting out something that's halfway between a high and a low for 100 clock cycles. Well, that's going to screw this thing up, right? So what do we do?
Put a counter, it counts the clock cycles, and every 100 clock cycles it sends off a tick.
Yeah, that's possible. So we could sort of gate this thing and say every time we want to look at the input, sort of disable this thing for 100 clock cycles before we actually take the value. And it turns out that AND gates are actually good at this. If this is a low, this could even be halfway between a low and a high, and this will still be a low. So I could turn this off for 100 clock cycles after the person has pressed the button to kind of wait for this thing to happen. And I could put a gate in here to not allow new button presses to come in during that time. And so I could sort of set this guy off, and this guy could go off and think about something else for 100 clock cycles, and then I can look at the output. That's a viable way to do it. But let's say that this isn't the Coke button, and we're actually getting a whole bunch of data in here. In fact, let's say that we're getting data that's changing almost as fast as the clock is there. Let's say it's changing every 4 clock cycles. How are we going to deal with it? How do we synchronize this data to that clock? So we can't wait around and not look at the output for that long. Other ideas?
Can we slow down the master clock at the same rate?
Well, if we slow this thing down, then we don't get to say in our book that this thing runs at 1 gigahertz.
True.
So that's no good.
But during the times of asynchronous input, is that constant?
Well, that is possible. Yeah, we can slow the machine down.
Some
Yeah.
sort of buffer.
Some kind of buffer. What if I were to put 100 flip-flops in a row here? In other words, make an assembly line, or what we call a pipeline, of flip-flops, all clocked by the same clock. Now, if you remember, the probability of this thing still being metastable after 1 billionth of a second is not sufficient, right? We have to wait 100. But it is lower then the probability that this thing is somewhere in the middle, because it has had some time to try to converge one way or the other, to move the donkey towards one bale of hay or the other. Then we pass off the job to the next flip-flop. We say, okay, I've moved the voltage this far, and now I pass the job on to you. And now you move the voltage a little further. Now I pass the job on to the next one. Now you move it a little bit further, and by the time we get to the end of the chain here, we've had 100 clicks to do it, or 100 billionths of a second delay between the input and the output here, and the probability that it is still somewhere in the middle is extremely low. And so I can build myself a pipeline of flip-flops like there and basically hand off the task to the next flip-flop in the assembly line to get the job done. That's one way to do it. Another way to do it, which is equally valid, is I can have 100 flip-flops like this, okay? And I can have a decoder over here and a multiplexer over here, and I can basically be sort of doing a round-robin scheme like this, where these guys are only clocked at 100th of a second, and I basically go around and around like this, and each one of these takes a part of the job and takes 100 billionths of a second to get this done, but the next job is given to the next one 1 billionth of a second after it's given to this one. So I could give you a job, saying, start figuring this out. Then the next billionth of a second, I give you the job, and I give you the job, and then by the time I get around to you, I've gone through 100 students, and you've had 100 billionths of a second to get the job done. And so this is an alternative way of spreading out the job amongst 100 flip-flops. Okay, and both of these are in fact used when dealing with asynchronous inputs from the outside world, as well as the other methods of slowing down this clock here or gating it and just kind of being blind to it for a certain length of time. But you've got to do it. And back in the 1970s, in fact, as early as that, there was still debate as to whether you could solve the problem another way. And articles appeared in journals with circuits saying, aha, I have solved the arbitration problem, and here's a circuit to do it. And the next month would come a proof that that circuit can be metastable also. And it went around and around and around for roughly a year. And there's still no actual proof that you can't do it. Okay? There is a proof that if you assume the circuits are continuous and time invariant, which you guys may know about, then you can't do it. Okay? But physics is, kind of allows you to have more than that. And so there's still no proof that it can't be done. But so far, there hasn't been a circuit that can do it. Okay. Big question for the end of the lecture here. Is this an excuse for cruising a light? So the typical thing is, of course, the light changes from green to yellow, or depending how you drive, from yellow to red, right? And you need to decide whether or not you're going to stop or whether you're going to go through. And if the light turned to red before you got to the intersection, you're supposed to stop, right? And if it turned to red after you went through the intersection, you can go through. And so this is a metastability issue as well, okay? So the question is, can you use this as an excuse in court? You say, I'm sorry, officer, or I'm sorry, Your Honor, right? I was in a metastable state, and by the theory that I've learned in Ars Digita here, that one can stay in a metastable state for an indefinite length of time. And the yellow light is only on for 2 seconds, right? And 2 seconds is a long time, and the probability is very small, but it's not 0. And that's true. But of course, what does the judge say? You get 10 to the 30th years. So, okay, great. Here's everything that we learned. I think I've been talking a long time, so I'm not going to go through this, but you all can read it on your own.